Yeah, the next topic is Nernst equation. Well, this equation relates the um, the electric potential with the concentrations. Okay, under the standard conditions, we've already you know, learned how to calculate or how to measure that the standard reduction potential. Yeah, but mm, actually, the experiments are done not under the standard conditions, but under the various conditions. Okay, so this Nernst equation now dictates mm, how this potential changes with concentrations. Okay, the Barton Nernst was a very famous physical chemist, and he was awarded a Nobel Prize for this work. Um, Here, net driving force for electrochemical reaction is expressed by Nernst equation. Um, Actually, this Nernst equation is very rigorously derived from thermodynamics. Okay? As you saw, the electrochemistry and thermodynamics are very closely related. For example, delta G equals minus NFE, right? And let's see, there are two terms, driving force under standard conditions, okay? That indicates the potential is E0, okay? And also another term is driving force depending on reagent concentrations, okay? Now, the natural question is how E changes with concentrations, okay? So this equation now relates the E and this concentration. Let's consider this half reaction. Mm, And the rest equation is given by this one. Okay? E equals E0 minus RT over NF, and this is the natural logarithm. And this activity of P and P power n divided by an activity of A and A powered. Okay, so quite simple actually. And here, this ratio is defined as a reaction quotient. Okay, reaction quotient. Reaction quotient means that uh, this ratio, yeah, or under any conditions. Okay, but when the reaction is at equilibrium, this Q becomes K, equilibrium constant. All right. Where here the concentration is expressed by molar concentration, mole per liter. Okay. And when this reaction contains the gas, and then we use gas pressure in bar, okay, bar, or atmospheric pressure. Now, 1 atmospheric pressure is almost 1 bar, but exactly 1.013 bar, right? When all activities are unity, Q equals 1 and Q log Q equals 0, thus giving E equals E0 or E naught. Okay, yeah, so everything now makes sense. So now usually we are working at a room temperature, which is 25 degrees C, and instead of natural logarithm, we use this one, this common logarithm. Okay, in that condition, the nearest equation becomes this one, E equals E0 minus this one, 0.051916 volt. This unit is volt, divided by n log this one, this ratio. Okay, so this means that the potential changes by 59.16 millivolt for each factor of 10 change in log Q. Okay, when this ratio changes ten folds, and then see, and when n equals 1, the potential changes is 50 about 60 millivolts, right? Here is an example. Let's try to write the correct Nernst equation for a half reaction. This one, this phosphorus, this is called white phosphorus, okay? And it reacts with this one, proton and electrons becomes pH3. Okay? This is gas, and E0 is already known as minus 0.046 volt. The next equation is written in this way. Yeah, this is E0 minus this one 0.05916 divided by 3 log this one. This is product side, okay, here. Since this is gas, we instead of molar concentration, we write this pressure, okay. And here, since on the reactant side, the phosphorus is a solid, okay. So usually we don't include the solid concentration in the equation. Only the proton concentration here, like that. Quite simple. Yeah, but here is there is a very important aspect uh, in here. Okay, and now we wrote this equation like that. Yeah? But if you multiply on both sides by 2, and then this one is 1/2. Okay, and not 3 protons but 6 protons and 6 electrons and 2 phos uh, pH3 the gas, okay, but the electrode potential this one doesn't change at all, not changed, okay. This is very quite important, you know? And you'll see soon uh, this potential is a intangible property, which means that property, intangible property, is defined by that although the quantity changes, the property doesn't change. Here, by multiplying the both sides by 2, you change it, the quantity, okay? But this potential doesn't change at all. This is important. But what changes? Energy changes, okay? You see, delta G equals minus NFE. Yeah? Delta G is extensible property. If you have more quantity, and then that property also uh, increases, yeah, in proportional to the quantity, okay, but the potential doesn't change at all. Yeah? So for this one, the lower uh, you know, reaction, we can write this way, okay. E equals this part is doesn't change. For other part we use 6 electrons, all right, and this one, this pressure squared and divided by proton concentration, you see 6 power, okay. And as you know, from the log property, right, this one 2 and 6, yeah, it can be a third power, and this is simply p, and then 2 now it's cancelled by the 6, yeah, and the 6 becomes a 3, and we have the same Nernst equation here, okay. That's quite important, okay? And then let's consider why the potential doesn't change with the change in quantities. Potential difference between 2 points is work done per charge carried through, okay. Here the potential is given by this equation, work divided by q, all right. Therefore work per coulomb is always the same whether, yeah, 0.1 or 2.3 or 10 to 4 coulombs of train charge has been transferred, okay. This one, this potential, uh, so although you increase this work and the charge, they increase both, right? So the potential doesn't change at all. Okay, and from now on, we are going to use Nernst equation to calculate the cell potential. Yeah, right? The Nernst equation for the complete cell. So now we learned how to write Nernst equation for half reaction, but the complete cell consists of anode and cathode. Okay, so how do we calculate the cell potential using this Nernst equation? First, you have to accept this one. This is cell potential E, or electromotive force. Okay, E equals E plus and minus E minus. Okay, what is E plus? This is the cathode potential. Okay, yeah, from now on you have to be very careful and listen to me very carefully. Uh, you know, I will show you the simplest way to calculate the cell potential. Okay, first of all, you have to accept this equation. Yeah, cell potential is the potential difference between cathode and anode. Okay, anode cathode potential minus anode potential. Mm. The procedure here are procedures for finding E. First, write reduction, half reaction for both half cells. I'm sorry, this is half. Okay, although no, at the anode oxidation takes place, but you have to write anode reaction in reduction form, and then later on, simply by taking this difference, and then everything will be corrected. Okay, right Nernst equation for right half cell, this one is right. Okay, and then write the Nernst equation for the left half cell, right, which is E sub minus, right. Important is that you have to mm, uh, write the reaction in reduction form. All right, find the net voltage by subtraction. Okay, by taking this one and subtract the left half reaction from the right half reaction. All right, to write the balanced net reaction. Okay? And then if uh, calculated E is positive, the net reaction is spontaneous. And if this is a negative sign, and then the reaction is not spontaneous, it's non-spontaneous. Okay, here is an example. Okay? Let's consider this cell. Yeah? This is anodic part, this cathode. Okay, this is very simple cell. Yeah? And on the left hand side, cadmium metal inserted in the solution containing cadmium nitrate, and on the right hand side, silver metal is inserted in a solution containing silver nitrate. Okay, and then these two beakers are connected through a sort of bridge. All right, and then let's consider hmm, this reaction, the cell potential. Okay, and for the let's consider the right electrode reaction first. Silver electrode is silver, and then reaction this reaction takes place. Okay, here. So since number of electrons are not the same, intentionally here we multiplied two, constant two on both sides. But the standard reaction potential doesn't change. Yeah, 0.799. Okay, and left hand side cadmium reduction. Although actual reaction on the left hand side is the oxidation. Yeah? This cadmium is oxidized, which means it dissolves into the solution as cadmium, the ion. But you see, we simply write in the reduction form, and then we write the Nernst equation, and then finally we subtract this left hand side from the right hand this direction. Okay, Okay, and E sub plus equals this one 0.799 minus, okay, this one 0.05916 divided by 2. Okay, actually, and then this part, silver 1 over silver concentrations, squared. But if you simply write, if you ignore this 2, yeah, constant 2, and then this part will be ignored. But still here, this 2 and 2, they are cancelled out. Okay, and then we and then what's the silver ion concentration here? Yeah, you can see here. This is let me see from the textbook. Uh, the concentration is 0.5 molar. Okay, and then we calculate this what 0.7817. Likewise, we calculate the left electrode potential like that. All right, and then the cadmium concentration is 0.01 molar. Okay, and then we got minus 0.461 volt. So the cell voltage is 0.7817 minus this one minus 0.461, and then we got 1.242 volt. So this is greater than zero. So this overall reaction right here, overall reaction, you see. So since the electron reaction is written in a reduction form, so we to get the total reaction, net reaction, we subtract the first one, this reaction, minus this left hand, the left electron reaction, then we get this one. Yeah. So this reaction takes place spontaneously. Yeah. Here, cadmium just keeps being dissolved into two cadmium and ion and silver ion, now reduced as a silver metal. All right. Yeah. And graphically, we can write it this way. Yeah. This x-axis is the potential, and this one silver electrode potential. Now we calculated, which is the value is this one, 0.781 volt right here. And then this one, cadmium electrode potential here, minus 0.461 volt. Okay, here. Then this is the difference, right? And electrons flow from cadmium to silver. Okay, or currents flow from silver to cadmium. Okay, here electrons always flow from the more negative to the more positive electrode. Yeah? This is they always flow to the right in this diagram. Okay, flow to. Mhm. But current always flow from more positive to the more negative electrode. Yeah? What if you had written the Nernst equation for the right half cell with just one electron instead of two, like that? Since we wrote two here, right, to make a balance the electron, to make the number of electrons the same, but although we write this way, yeah, nothing changes. Okay, nothing changes. Neither E0 nor E depend on how we write the reaction. Okay, that's very important. Yeah, let's stop temporarily here. Okay?